Hello, everyone. So I'm Jason Molgaard, and along with Bill Martin, we'll give this presentation about CXL support in NVM Express. So briefly on the agenda, we'll discuss why would we want to combine these two technologies. We'll talk about computational storage as one use case, albeit not the only use case. We'll discuss the technical proposal that we're working on in support of this combination. And then we'll look at a couple of computational storage use cases in detail. All right, so why would we want to combine these technologies? Well, I think there's two key drivers that we want to consider. The first one is that NVMe devices are providing host accessible memory in the form of SLM. So this is obviously something new that we have talked about in the past, and there's lots of presentations out on YouTube if you're unfamiliar with it. But wouldn't it be nice with this memory that we have if we could access it with a memory protocol? And it would also be helpful if we could have coherency to that memory that we're now enabling in the device. And then likewise, it would be helpful if we could have peer-to-peer communication using a memory model with this memory. So that's one driver. The second driver is a computational storage use, which is not the only one, like I said. So from a computational storage perspective, there's more memory in the drive than a traditional storage drive. And so because of that, we've got this memory. It'd be potentially useful to access it with a memory protocol. And then a computational storage can certainly benefit from peer-to-peer communication. And we'll get more into this later. We have an example at the end of the presentation. So I would suggest that CXL actually checks a lot of the boxes of what we just enumerated of what we'd like to have. So CXL brings coherency to that memory and in the device and the host, so we can have those coherent accesses. CXL brings low latency, fine granularity access to the subsystem local memory. CXL.mem allows direct load store access to SLM. And then CXL also allows for peer-to-peer communication using CXL.mem. So you may be asking yourself, well, how is this different from CMB and PMR, which we already have in NVMe and has been available for quite some time? Well, great question. So CXL allows both coherency with host memory and MMIO space, whereas CMB and PMR is only going to allow load store access over PCIe uncached MMIO space. So you don't have the coherency. That's one big thing. With that coherency, we can have coherency with the host, we can have coherency with other devices that would not be there with CMB and PMR. And the CXL protocol is more efficient than PCIe memory access protocol. So we can have lower latency, higher throughput, and then also CXL has less strict ordering rules than PCIe. So just to kind of level set some general benefits of coherency, as I've spoken about coherency a lot and bringing that to subsystem local memory. So first of all devices perceive the same view of memory with coherency. We no longer have memory viewed, we have memory that is viewed as consistent between the devices, and that's what we want. All devices perceive the same view of shared data. So all the data is up to date. We don't have stale copies. Devices and hosts can push data to each other or pull data from each other. So this includes device-to-device communication, and we're able to send data to and from one another coherently. And then lastly, which I kind of already touched on, is we avoid or reduce copies that can grow stale. We certainly don't want to make copies that get out of date and become inconsistent, and coherency solves that. All right, so I'm going to turn it over to Bill, and he's going to talk through computational storage and also the NVMe T part that we're working on.
Thank you, Jason. So I'm going to start with a set of slides that have been presented previously. And these are available. They were presented last year at FMS. They've been presented at Storage Developer Conference hosted by SNIA The presentations are available on the SNIA website for sure, and I'm just going to briefly go through these rather than go into depth so that you have kind of a focus on this. So computational storage architecture is an architecture that was written up by SNIA, but it's being used in computation for NVMe. And in particular, we're focusing on the middle device here, which is the computational storage drive. And we're focusing on a small piece of that. So there are several components that are defined in computational storage, but in particular, there is the memory that is used for the computation to operate on, to store its results into. And in the SNIA model, that is called the function data memory, and then you have the ability to allocate function data memory within that model. So we're talking about how do you access that memory. In NVMe computational storage, we're using what's called subsystem local memory. And as Phil mentioned earlier, we've developed the subsystem local memory command set, allows you to communicate with that via NVMe commands. And we also have the function data memory, which is what is defined in the SNIA computational storage architecture, is equivalent to the subsystem local memory here. Now, one other concept here is that in the computational storage command set, we are able to put a memory range set that identifies specific areas within that subsystem local memory, and that will come into play a little bit later as I talk about how we are looking at mapping the memory so that we can use, instead of NVMe commands to access it, host load store commands. So let me get into what we're doing with TP4184, which is the NVMe name for this, and it's called Host Addressable SLM. So what does Host Addressable SLM provide? We are currently in the architecture phase, which means we're kind of defining what is the architecture for this. Okay, but what does it do? SLM is addressed as a host physical address. So it means that you can pass that host physical address in the commands that go to NVMe as part of your SGL, if you're familiar enough with NVMe to understand what an SGL is. So those host physical addresses can be passed in the SGL, and they can address this subsystem local memory that's on the device at a host physical address. Now, how can that be done? That can be done either through PCIe bar or through CXL. And Jason alluded a little bit to the differences between the PCIe bar access and the CXL access. We are, within this new proposal, making this memory accessible both ways. It will be sort of like CMB, and it will have some of the same characteristics as CMB, but that's still the architecture. Part of this is exactly how it compares to CMB and how it's different from CMB. It will be accessible also using the NVMe command set, so there's two ways of accessing the memory. What this allows is that the SLM can have a virtual mapping for host applications, so they don't have to switch context for SLM memory accesses. So when you are trying to store your data for your application on your host that you want to compute on, you store it into host physical address space, which ends up being on the NVMe device. So now you can immediately utilize that, and you haven't had to do a context switch to do an NVMe memory write command, where you don't have to switch context to do an NVMe memory read command to get it back into the host. So this memory is now accessible by both the host and the device. It can be read and written either with the host load store commands or with the CXL.mem command. So that allows either the CXL access or the PCIe bar access. That will be determined by the device as to which type of access you're using. You will use one or the other. You won't be using this both as being in a PCIe bar space and in a CXL host physical address space. It will be one or the other. So compute that I talked about on the previous slides is triggered using the Computational Programs Command set. So the Computational Programs Command set is used to send an execute command, and in that execute command it tells you what portion of the subsystem local memory are you using for this compute. So Jason will get a little bit more into details of a couple of use cases for using this that will really kind of highlight that. The other thing that this new feature in NVMe is intending to allow is peer-to-peer data movement based upon a host physical address. So now if I have two NVMe devices, each of which have a host physical address that's mapped to the device using CXL, I can pass the host physical address of the other device to the device that's executing the command, and that command now allows that device to send the data directly from that device to the other device using the host physical address that uses the mapping structures of CXL. So SLM is still accessible using the SLM command set, memory read and memory write commands. Didn't get it on here, but it's also accessible using the memory copy command, which allows you to copy data to or from the SLM from your device storage. So how does this work in the system? This is a potential config flow for CXL SLM. It's not the only way. It is one of the things that we need to do as we put something together for NVMe is that we need to make certain that there's a mechanism within the ecosystem to utilize that functionality. So this is a proposal for how you can configure your ecosystem to make use of this functionality. So an NVMe device with CXL is similar to a CXL Type 2 device. We will use the characteristics of that to map this into the ecosystem. So the plan for CXL Type 2 devices is for the operating system to do a standard PCIe configuration. So for example, they will set up bar space on the device. You have to have that bar space whether you're a CXL device or an NVMe device. You have bar space for various things that you have to do for configuration, etc. So that will be set up. In a typical CXL Type 2 device, then then you would load the driver for the CXL configuration using the device's PCIe ID. For the NVMe device with CXL SLM, we would have an enhanced NVMe driver. The device will look like an NVMe device. It will not be an NVMe and PCIe device and show up as two different functions. It will not show up as a CXL function. It will show up as an NVMe function. So the enhancements will be based on the SLM configuration. So the device will use existing NVMe class code, may use a new programming interface to expose the CXL capabilities. The device driver, the NVMe device driver, discovers the CXL capabilities. It then calls what's called an OS CXL core services for CXL memory setup. So the NVMe driver now calls this for this host services, sets up the addressing, etc. for that SLM space. So the device CXL memory allocation, though, is controlled by the NVMe driver. So after the operating system configures the CXL host physical address space, that address is reserved, and that's part of the Type 2 similarity of this is that address space is reserved for the NVMe driver. That address space isn't just thrown out into the overall CXL host physical address space that anyone can use. It has to be allocated by the NVMe driver. So the NVMe driver is doing all of the allocation of that to applications that are attempting to utilize the SLM space. So Linux support is not yet available for Type 2 devices. There are mechanisms to have bypass commands that allow you to do all of this. And then in terms of the runtime management of the device CXL memory, again, the NVMe driver owns that runtime management. So how does this look in the system? And by the way, the slides will be available later that have the diagram on the right of that last. That was kind of a visual so that you can see kind of the flow chart of what I just walked through verbally. So in this, what you'll see here, it's a little bit complicated, but on the far left of the slide is how you would address a memory range for a specific compute command. And you would have a namespace ID and you'd have an offset into that namespace ID. That namespace ID is pointing to an SLM namespace. A couple of characteristics of this. Number one, very important, all of the CXL addressable SLM is going to be contiguous in the host physical address space. So there's not gaps in it that's used for other things. It's all contiguous within that host addressable space. So that then goes to the HDM decoder. The HDM decoder has individual decodings for each SLM namespace that has a host physical address base and a size. That then maps into the host physical address space. And as you can see, the light blue is a segment within that happens to represent a memory range that's used for compute, could be used for other things, and that maps into then a certain piece of the host physical address space. That particular light blue piece of this is then able to be provided to the application as a virtual address that then accesses the SLM address space. So really quick overview. We will be presenting this again at SDC, where we may get a little bit more into detail because we'll have a little bit more time, but kind of giving you a taste for where we're going with this. And now I'd like to turn it back to Jason to go through some use cases of how you use this.
All right, thank you, Bill. All right, so let's take a look at a couple of use cases that we have identified. So in this first use case, let me kind of set the stage by describing the diagram that's over on the right-hand side a little bit. At the top, we have a host, and underneath that, there's a CXL fabric that is connected up to this happens to be a computational storage device or drive. The next example will actually be more like a computational storage processor. On the left-hand side shows a picture of the host physical address space and the portion that's been allocated in the CXL SLM and where our host application is actually going to perform the operation. So this example is a data post-processing before writing to storage. So in other words, we're going to send the data to the drive. It's going to do some kind of a computation on it before actually writing it out to the persistent media of the drive. We have an input and output data buffer in our configuration. In this case, the input data buffer is in the SLM portion that is CXL accessible. The output data buffer is just in the traditional SLM. All right, so what happens is the application writes or does a store to the input data buffer using CXL.mem. At the end of the write, some of the data may still reside in the cache of the host. That's okay. The host then issues an NVMe execute program command for the Computational Programs Command set. So we're going to perform our computation on the data, processing it from the input data buffer and writing it to the output data buffer. That's shown in step 3. So as part of that, we need to make sure we've got all the data from the host into the device. So the device is going to issue a CXL back and validate snoop to the host saying, please make sure I've got all my data and invalidate your copy because I'm going to perform a manipulation on it. That happens, we get all the data in our drive now. The execute program completes and reports back to the host a completion. When that completion is received, now the host can send an NVMe copy command to move the data, to copy the data from the SLM output buffer into NVM, and into an NVM namespace. So it actually writes the data to the persistent media then, and a completion is issued back to the host. So I know it's a little bit difficult to see, but there are, each of these numbered steps corresponds with a number on an arrow on that diagram, and the slides will make it a lot easier to see when you're able to download a copy. So let's take a look at use case number 2. I'm sure you can envision a use case that would be very similar to the first one, where you'd have just the opposite, where your output data buffer would be in the host addressable SLM that you could access with CXL. This use case actually puts both the input and the output buffer in the host addressable SLM. And the key benefit of this use case is that we're going to bypass the host for data movement. And we're going to use a traditional SSD as our ultimate destination for this transfer. All right, so basically, as I mentioned, both the input and the output data buffer are in the host addressable SLM, so we can access it with CXL potentially. Very similar to the first use case, the host is going to perform writes, the host application. It's going to do those writes to the address space of our input buffer. Some of the data may still be in the cache at the end of those writes. Again, not a problem. Host then issues an execute program command. So we're going to process that data from our input data buffer into our output data buffer. And if necessary, then there's going to be a back and validate snoop from CXL to request that the host send all of the data to the device. So we get all the data, we're all coherent, and the host copy is invalidated. So it doesn't have anything that's not supposed to have. We're going to perform the computation on that data and write it to the output data buffer. Now that we have written that to the output data buffer, the host is going to issue an I/O write to the SSD NVM namespace. So to the left, we've got an ordinary SSD. The data pointer is going to point to the output data buffer in our host addressable SLM in our CXL memory space. And so then that write is going to read the data from our output data buffer, and using PCIe UIO, we'll do a peer-to-peer transfer and send the data from the SLM over to the SSD and write it into the persistent media of that SSD, and then send a completion back to the host. All right, so to kind of conclude our presentation, so we think that CXL and NVMe technologies can be used together, and certainly CXL brings load store access to NVMe SLM for sure. And through the TP4184 work that Bill and I and others are working on, we will be able to support that CXL access and all of the I/O command sets, including computational programs. Some of the key benefits, of course, coherency being a big one. So now we have coherency with the device SLM and the host. We have the lower latency and small data transfers that CXL provides. So if you don't have a large volume of data to move and you just want to do a small transfer, CXL is a great fit for that. Since the SLM is addressable via a host physical address, we don't have to copy data from host memory into the device. We can simply have the host write to it directly. And we can bypass the host for peer-to-peer data movement. So kind of looking ahead, there's a lot of work to do still on TP4184. As Bill mentioned, hopefully we can get into a little bit more detail in future presentations, and we certainly will. And this is the first step in enabling the intersection of NVMe and CXL.